challenge problem number 2, droplet microscope.
Number 2.
Would like to accept. Thank you.
Okay, number 2 accept.
还没有放上去，因为2月才入职，新还没有印好，所以中央这个没有谈论。
还好，
就这个学期，
就是冬天，
那接下来课程就也是反弹，所以这个
所以我们刚才单子给错了。我刚才是不是后来看到？
Okay, reporter, please.
Honorable judges and worthy debaters, this is Team Me2 reporting problem 2 droplet microscope. And here's the problem statement. By looking through a single water droplet placed on a glass surface, one can observe that the droplet acts as an imaging system. Investigate the magnification and resolution of such a lens. Our focus is on the explain the phenomenon, discuss different parameters, and what makes the droplet lens with better magnification. And here's the phenomenon. And this is, we assume that there's a point under the glass surface, and when the light reflects from this dots, the light will refract from the droplet and in turn have a image distance under the glass surface. And our relevant parameters is about the thickness of glass and the wavelength of the light source and the droplet shape. And in theory introduction, we use simple geometry. We can know that the magnification are equals to the object distance over the image distance, and we got these formulas, and we know that the object distance is equals to the thickness of glass and the droplet height in the certain position of x-axis. And deriving focus and the lens maker equation, we can get the radius of curvature in different position of the droplet. And because the radius of the glass surface is nearly infinite, so we can cross this out. And we can get the magnification while using the previous formula, and the assumption of this is that it is a thin lens condition. And next is about the resolution part, and we use Abbe's equation that can know the connection between the wavelength, numerical aperture, and the resolution, like these formulas. And we know that if we decrease the alpha angle, and we can decrease the sine value, and in turn we can increase the resolution of it. And if we increase the wavelength, we can also increase the resolution of the image. And by combining the formulas of magnification and resolution, we can notice that in this part we add up the thickness of the glass, and we can know that the alpha angle is smaller, so that the resolution is bigger, and also the refractive angle is bigger, so that the image might have bigger magnification. And as this part in the droplet of this different position, we can get different radius of curvature of it, so that we can also know while the magnification increased in the smaller radius of curvature, we can know that the alpha angle is smaller, so in turn we can have bigger resolution. And to sample out the droplet model, that we assume the height of the droplet in different position. We know that the contact angle of the droplet is equals to these formulas, and then this is the surface tension in different area surface of the droplet, and there will be the air and the water and the glass surface, and this is the assumption equation that we assume the droplet will be, because there will be only two indicators that shows the equation. So we just use an equation with two indicators. So this is our assumption of the droplet shape. And when we drop a droplet on the glass surface, we'll notice that there will be different curvature in different position of the droplet, and due to the various curvature distribution, we can get different magnification of it. And here's our experiment setup. And by changing the volume of the droplet, we can know the equilibrium state of the droplet will differ due to the surface tension of the glass surface and the gravity force, that it will be flat, while the volume of the water droplet is bigger. And by comparing our theory that we got in the previous PowerPoint, and our data, that we compare the curvature between our data and our theory, and we can see that it have positive correlation between the theory and the data. And the 30, 40, 50 are to be the 30 microliter of the water droplet, and we use the pipette to measure the precise volume. And while another experiment of the wavelength is we use the different paper to counter the different wavelength and the color of the light source. And in this graph, we can notice that if the lesser the wavelength is, the more diffraction angle it have, and in turn they have the bigger magnification. And here is our experiment results, that we can know that the blue ones in different position of the water droplet can always have a bigger magnification than the red ones, than the red light source. And another experiment is about the thickness of glass, so that by increasing the thickness of glass under the droplet, we can also see that there will be a bigger diffraction. There will be a bigger diffraction length while the light coming out of the glass surface. So we can know that, we can predict that there will be a bigger magnification of it. And here is our experiment result, that we use 3 millimeters of the thickness of the glass and 6 millimeters of the thickness of the glass. So we can know that the 6 millimeters can have bigger magnification. And as the previously equation we shows, we can know that if we increase the thickness of the glass, the magnification will decrease. But in this assumption is that there won't be the glass diffraction. We didn't consider this model to be the glass diffraction angle and the distance. So we improve our theory, and that there will be a geometry figure shows as this, and we can know that while we increase the thickness of glass, and we can get the bigger magnification. And in conclusion, after the 3 experiments of the thickness of glass and the wavelength of the light source and the shape of the droplet, we can also see that these 3 factors affect the magnification of the droplet's imaging system. And as the equation shows below, shows previously, that we can also know that if the magnification increase, the sign value of the diffraction angle will decrease, and in turn cause the resolution to increase. Thank you.
Okay, opponent.
So first, can you turn your presentation to the page where you did a line that looks like this?
Yeah.
Can you explain further, like what is the x and y axis supposed?
The x-axis is the droplet axis, and we use the
Okay, I see. Then can you turn like then what experience do you do with the different thickness of glass? Like what do you do, like the magnification or resolution?
I investigate the magnification of while I change the thickness.
Then do you have the graph?
Yeah.
Okay, so then do you have a picture of your whole setup?
I did.
So you don't have a picture of the whole. So you don't have a picture of when you set the whole thing together.
Yeah.
Okay. And can I ask, like, for the camera, you use, is that a phone?
Yeah, it's a phone.
It's a phone. Okay, thank you. And then can I look at the? Can I ask that did you control the volume of the every time you drop on the glass?
Yes, I use, as I previously said, that I use the pipette to control
And
the volume.
then so you did it like only with hand, right? So
Yes.
Okay. And I think that's all for my question. Thank you. of this, and I'm from team of Orals, and I will be opposing on the question droplet microscope. So first, we'll be talking about a problem statement. By looking through a single water droplet placed on a glass surface, one can observe that the droplet acts as an imaging system and investigates the magnification and resolution of such a lens. And the reporter mainly focuses on the phenomenon and and use different parameters to test out the magnification and the resolution. And okay. So a brief summary for the reporter. Their observation and theory, they use the Ab's equation and Lensmaker equation and use different and fitted a function for the curvature of the water droplet. And for the experiment method, they change the thickness, wavelength, and droplet shape. And for the data analysis, they think that the thickness increase, the magnification will increase. And if the wavelength decreases, the magnification will increase. And for the conclusion, they say that the thickness, wavelength, and droplet shape are the main factors for the magnification. For the pros and cons of the reporter, the pros is they have clear demonstration of the phenomenon, and they have organized results and data, and consider different various variables. And for the cons, they try to connect the theory. They can try to connect the theory to the experimental results, which I'll elaborate further. And they have a lack of experiments of the results, and they didn't introduce the experiment method inside of their presentation. So for the discussion with the reporter, for the theory, I will be discussing on whether the lens maker will fit in your theory, and I'll say it later. And for the experiment method, I want to mainly focus on the environmental light of will it influence the magnification, or will it influence the resolution, and explain how. I want you to explain how the experiment works when you use the feng shui report. Will it have an effect? And I want to ask how the same volume droplet will vary the shape, and how to control the location of the drop. And for the extension, I wanted to ask that is whether droplet you think is a thin or a thick lens, and want to ask for the definition of your resolution. So I want to invite the reporter onto the stage. So first, I want to ask my first question is that, do you think that, when you do this experiment, do you have an experiment when you test out different, like you have pictures of different resolutions?
In our hardware, we don't have the equipment to test the resolution.
So you don't have the way to test resolution. Okay. Then can I think I can introduce a way. It's called an optical resolution. Which for optical resolution, you can use for example, if you want to use a camera. Okay. For example, you use a camera, and then you take a picture of maybe like gridded dots. Then when like optical resolution is mainly talking about if the dots, like whether you can differentiate these two dots. For example, when you look in the camera, you can actually differentiate these two. Then for example, we call it that this is a good resolution. And then we'll keep doing it until when we cannot differentiate them. I think that is a way for experimentally you can define how good a resolution is. Do you agree?
Yeah, I agree that. Here, I also use the method that you have mentioned that I think it's called the relay criterion. Yeah. So this is my theory. So maybe I should use the dots that. Do you mention that you need to get the dots closer every time you?
Yes, use different size of the grid. Like for example, maybe the grid is, I will use the dots to be like from maybe this big to to smaller, and then we use the camera to investigate that.
But I want to know that how do you define that if the dots are overlap with each other?
Well, okay, so can I use the blackboard? Is for example, for example, maybe there is like a grid, and maybe with the magnification, you see this is the magnification of it. So this is the water droplet.
Yes.
So maybe you see grids like this. So you can identify these stuff, right?
Yes.
They are different. Or maybe, like for example, if you use like a red wavelength, which the resolution may be like worse, then maybe the grid like it will be blurred like this. Maybe it will be blurry, like you cannot see the grid and the dots. So
but in the I think in the equation I just give that if the wavelength increase the resolution. So why I don't know why that.
wait, do you understand this equation?
Yes.
Because from my perspective, I think that if the let me see S is it
And
the
sine.
A is the angle, right?
Yes. Okay.
So angle is the differential angle. For example, like if I want to differentiate this, for example, maybe this circle, then like the light, this is the light, and then when it goes into the lens, there is this angle. This is your A.
Yes.
So if this angle is larger, that means that you have to be closer to see the whole circle.
Yes.
So that means if you have larger A, which means the angle is larger, that
Yes.
means the resolution should be worse, right?
Yes.
Which means that if you move A to this side, so if your
It's a constant. Assume that.
Yes.
Assume that.
Yes, other constant. So if your wavelength is larger, for example, from blue light to red light,
Yes.
from blue light to red light, right?
Yes.
Then shouldn't this increase, right?
Yes.
So if this increase, the angle should increase, right? Because this is constant.
I don't know why this is constant.
Then can you explain what do you think S means in this equation?
I think that if we change these variables, we can get.
Then can you explain what S is in this equation?
S is like we previously just said that if we use two dots to investigate how we differentiate
Yes,
these
yes,
two
yes.
dots, that if the S is larger, we can see we can differentiate the two dots from a bigger range of the visual.
So S is this?
Or no, S is kind of the value that if the S is bigger, that I can differentiate these two dots with a bigger visual distance.
Okay, I think we don't have like maybe we use different equations, but I think maybe like there's a misunderstanding with this equation because in my perspective, like these when you're using the same length, that these three variables should be the same. So I use these two as the main.
You mean what?
Like I mean, if you drop the same amount of volume, the shape is the same, right? So these three variables should be the same from my equation. So I think that when the wavelength is larger, this will be larger. But I think I will go to my next question. Is that so in the experimental setup, you say you use a phone to
Yes.
take a picture, but do you know that when you use a phone, like
The resolution will be the same.
No. I think yes, resolution will be the same also. But do you know that the phone inside of the mechanism, the phone also changes its own focal length, so you can take a better picture.
But our
Like, do you consider?
Our goal is to investigate the magnification between the dots I draw on the
Yes,
glass
yes.
surface and under
Yes,
that water droplet surface.
Yes, I know. So do you think the I inside the phone, like there when it changed the focal length, like maybe the light, it might not go like, for example, this is the imaging service of the iPhone. Maybe it's not clear, so it will have it will have its own lens here, so it can change the focal to make it clearer. Do you think this will affect?
I think that the mainly effect of the magnification is the focal length of the water droplet.
So this is not very measurable.
Yeah, it's not very measurable.
Okay, but from my perspective, I think you can use, because there are also apps that you can lock, like you can make sure that this doesn't change. I think you can also use this to try taking some pictures and see if there is actually a difference. But I think there will be
You
an
mean
effect.
if I control these
Yes, because
the value?
there are
with
apps.
the the
Yes.
bone and the drop.
Yes, I
Thank
think
you.
yes, I think you can try to do that. And next, I want to ask that when you drop the droplet onto the glass surface, how do you drop it? Can you, for example, like this is the surface, then how do you drop it?
I drop it like perpendicular to the
Yes.
the
So then
surface,
can you show me your observation video?
Do me this
Yes.
or this one?
The bottom, that one. Yeah.
Yes.
You can see that first. Okay. From my perspective, what I see is this is your surface, right?
Yes.
And your droplet is like this. There's already a droplet on it, right? I think there is already a water droplet on it. And I see like when your pipette is a little bit like to the side. So when you drip the water, it moves the water droplet from here, and then it moves a little bit like this. Do you agree?
Yeah, but okay.
Yes,
as a
okay.
result of that, I
Then
think
do you think?
maybe we need to use a bracket to control the.
Yes, I think
Yeah.
like from an opponent, I think you can use, for example, maybe you can drill a hole so that your pipette can go through like this. And
So
then
you mean the
yes,
when
your
you
pipe, yes, because
stabilize
the pipette. So when you drip it, it will be on the same location and it won't move the water droplet to the side to change its own shape. Because that's what my next question will be, is that because if you don't drop it at the same place, do you think it will? I think it will affect the shape. Then do you think that the affection of shape will affect the magnification?
Can I try?
But you drop.
I think when I add the pipette to the instead of the middle point, I maybe have the little
Yes.
little error of it.
Yes.
But I
Yes.
think
Doesn't matter.
it does not really matter because it will be the same shape of the droplet when.
Yes,
the-
but then I want to ask you the question.
and
okay, you first.
and because that I consider it that the factor is
Very small.
Very small.
Okay. Can I ask you the question?
So
Is that can you go to the page where I said you fit the curvature to
Yes.
the X? Okay. So from this fitting, I see a big. I have a question. Is that, for example, like this fitting is the drop. Is this experimental value?
yes.
Then why? Can you explain why this is so much farther than this one?
In this figure, you can see that because of the model that we use I think is incomplete while in the droplet in the margin of the droplet because we use the polynomial to fit the curve
Yeah,
so that
so do you
it'll have it might have the bigger radius of curvature while in the margin of the droplet so that it will have the
So can I ask you a question?
Yeah.
What do you think causes the error? Is it
causes-
experimental or is it a theoretical problem?
I think the experimental might be some
Okay, but
yes.
yes, okay, I agree with you too. Yes, I think that's the end of my question.
Thank you.
Oh yes. Okay. So to summarize the discussion, I discussed with the reporter on how would they test on the resolution and gave advice on many parts of the experiment where they could, for example, the camera or the resolution or the experimental setup. Like what can they do in order to stop, in order to minimize the error? For example, for their pipette, I think they can drill a hole or use a cross to make sure that the droplet is dropping at the same place every time. So it wouldn't cause error or make fitting be bad. And for example, for the resolution, I gave an idea of optical resolution, which is the Rayleigh, which is a Rayleigh's way of defining two lights, two dots, and see if they can differentiate it to see whether the resolution is good or bad. So I think that so that summarized the whole discussion. Thank you.
Okay. So review.
So firstly, I would like to ask from the reporter, so why isn't your theory fit your data?
I think it's our, as the reporter just said that we might control the pipette and in the
So you think that it's because of your experimental setup?
might be some error to the, might be some different to our fitting line, but yeah, I think.
So how about the opponent? What is the relation between the magnification and resolution? Is proportional or disproportional?
You mean both? I think they don't have a clear relationship because they have different factors.
Okay, so how could you both define the resolution? Is the clearness or the amount that pixel you can see?
I think the best way of course using the pixel you can see, but for experimental wise, I think using pixels will be heavily affected by your camera. So I think using the other ray-less way would be better.
So do you think that if we consider the cameras, the resolution of the cameras, so we can correct the amount of the pixel amount?
Yes, I think agree.
So do you both consider about the spherical operation?
Yes, I think for the experiment, if the fitting is like of the curvature is like that means maybe it's not actually a like it's not like x to the power of 2. So I think there will be spherical aberration.
Okay. How about report?
Because that we only have when we did the droplet on the glass surface, we'll get the height, the maximum height of
Sorry, I'm asking about you. Do you think the spherical operation will affect the phenomenon?
Can you say that?
Spherical operation, will it affect the phenomenon?
You mean the surface tension?
No, thank you. So, what will decide the image whether it's virtual or real?
Wait, can you? I think that whether the object is inside the focal or outside the focal will be the main factor that decides if it's virtual or real.
So will it be demagnified?
Will it be demagnified? If it's outside the focal, it may be demagnified.
Is outside the focal or outside 2 times the focal length?
Oh, I think it's outside 2 times the focal
Okay.
length.
So how about the reporter? Do you think there will be a dismagnified condition?
I think in our experience that we investigate, we can observe that there will be we can know that there is no the upside down of the image, so that I'm sure the focal length, the object distance is less than the focal length.
Time's up.
Honorable jurors and fellow competitors, I'm the reviewer from Team Excelsior, and today I'm going to review problem 2, droplet microscope. For the problem statement said I placed a single wax droplet on the glass surface, so that will become a image system. So we would like to discuss the magnification and the resolution of such a lens. And we will mainly focus on how different parameters affect the resolution and the magnification, and how is object magnified by the water droplets, and what changes the optical characteristic within different parameters. For the review of the report, the reporter mentioned the phenomenon is the object is magnified by the droplets, and he used Lensmaker's equations, thin lens formula, and Abbe's equations as his theory. And he has 3 different parameters in his experimental part, which are the thickness of the glass, wavelength, and the droplet shape. And I think he demonstrated the phenomenon well and considered many theories, and also explained the curvature. However, he has the unclear illustration and lack of qualitative explanation. And also, he didn't talk about the resolutions and failed to explain the experimental data and lack of parameters. And for the review of the opposition, he noticed the lack of the experiments or resolutions, and noticed the unclear explanation of setup. And he also noticed the deviation that the phone may cause due to its automatic focal length change. But he didn't discuss the magnification a lot, and didn't discuss the angle of the view, and also the surface tension and the form of the image. And they also didn't discuss the spherical aberrations, which I think it will affect the phenomenon a lot. And the key discussion is the resolution. What is a good way to do the experiment on resolution? The reporter said they didn't do the experiment, and the opponent gave some advice to the reporter. However, we think the lens, the line pair per millimeter could define the resolution well. And the key discussion is the deviations. So the opponent asked for why is the deviation in the droplet shape of the experiments is so big. The reporter said that it's due to our fitting method. And I think it's because they didn't consider the droplet as an ellipse. And for our question, I asked for the spherical aberration. How will the spherical aberration affect phenomenon? And the reporter didn't answer, and the opponent takes a thing that will affect, but they didn't explain how will it affect. And for the next question is the image form. Say the reviewer say what will decide the image, whether it's a virtual or a real form. The reporter didn't answer, but the opponent said that it will depend on the distance, and the reviewer agreed with the opponent. And for the point missed, I think there are lack of the discussion about the resolution, which means the definition of the resolution if it's cleanliness of the image or the pixel we could see in per lens. And they also didn't discuss the parameters, which are the intensity of the light and the refractive index of the water and the air. And they also didn't discuss when the radius of the droplet change, how will it affect the thickness of the droplet or something else. And they didn't discuss about the shape control of the droplet. Thank you.
Thank you. Thumbs up.
About the concluding remarks, in the discussion with the opponent we discussed the optical resolution. We discussed the method that we can test the optical resolution, and we also discussed the Abbe equation can effectively derive the wavelength, numerical aperture, and the resolution. And I think that the Abbe's equation is the same, has the same concept and of the Rayleigh criterion. And we also discussed while using a phone to record does not might change our experimental result, but I think that the change is negligible. And next is we discuss our experiment setup that the opponent suggested us that we can stabilize the pipette to improve the accuracy of this experiment, and I agree with the opponent. And since we assume that the droplet is the reviewer asked us that how did the spherical have the difference, and we assume that the droplet is a symmetrical shape, so that we use 2D model instead of 3D model to fit our droplet curve. Then we can save a lot of calculation. And thank you.
Okay, thank you. Any question for Jules?
May I ask you a short question? That S, is that the separation between two object points?
I think this is S is the resolution.
No, S stands for what?
Resolution. You mean S?
Yeah,
Yeah, I think it's.
the dimension is wavelength, it's the length.
I think that.
Isn't that the length, the separation between the 2 points you're looking at?
Professor, may I ask the same question for Paul the pin? What's the meaning of S? Can you answer the question?
I think the opponent should have a chance because he asked in detail. What's S stand for? No, I don't want to ask him because he didn't understand the relation between F's formula and radius criteria. Actually, they are the same.
Yes.
For microscope, you can derive the same. It's using a numerical aperture. That S just stands for separation. If you see the dimension, it's length.
Yeah. Oh, yes.
So, what's the meaning of S?
I think according to the professor said that I think it will cause the contrast of the lens, and it will define the resolution for a little parts, but not all of the part of the resolution. Since
What's the S is have a unit of length, right?
Yes.
How is that related to the resolution? What's
So,
the meaning of this?
If we could have the higher resolution, so we could see the shorter lens to become a longer lens in our view.
Okay.
More clearly, and we can see more pixels in our view.
More pixels. Okay. And so, can you explain again?
Because I think that we think that this is the minimal the minimal length that we can differentiate between the two dots.
Okay.
Yes.
Okay.
So I would like to follow these questions in the spatial resolution. This is called the spatial resolution of the water droplet microscope. Spatial resolution. So for the opponent and reviewers, what is the maximum spatial resolution you achieve in your experiment? What is the maximum spatial resolution achieved in your experiment? Do you have a number?
I observed the 41 m resolution.
41 micron. Mu n is micron.
Yes.
41 micron for your experiment. That's a spatial. How about
I think it's millimeters.
41 millimeter spatial resolution? The opponent?
Because for us, we didn't use that formula. We used another formula, which I think I misunderstood for the formula in the bottom. So what we get is an angle.
Oh, you get the angle.
Yes.
Thank you. Angle is the same. Spatial.
Okay. Any questions?
So if not, I feel like ask. You use the lens maker's formula, didn't it?
Yes.
But you have a glass plate under the water drop.
Yes.
So does the plate, the glass plate, change the path of the instant ray?
Yes, so we change the thickness of glass so that we can.
But should be included in your
Yeah.
image system.
We have to include the thickness of glass into our.
It is not a simple lens, it's a complex lens, you know. Except the first one is two curvatures.
Yes.
It's plane, so the radius curvature is infinity.
Yes. We have mentioned that.
You mentioned, but that should be included in your theory. If the ray is not normal to the plate, it has effect.
Yeah, so that we point out that.
No, that's just for the water drop.
Yeah, water drop.
I'm not asking you the.
But
Okay, you time's up. All time's up.
Okay, so
I actually should ask both of them because they didn't mention anything about this, and I was surprised.
So I think we can have more comment after.
After we.
Okay, so please yours, give your call.
First thing first. Who's good, Mark?
So okay, let's give score of reporter. 556. Okay, 5 average. And the opponent. Okay. 7, 6, 8, 7, 6. Okay. And the reviewer. F7776. Okay, good, thank you. Take a break.